This has been my honors project, and we looked at the effects of different algal feeds and temperatures on survival of post-settle juvenile Tripneustes gratilla sea urchins, which has implications for the potential establishment of a sea urchin aquaculture industry in South Africa. So why sea urchins? Well, the gonads of sea urchins are eaten, and they're a highly lucrative delicacy, specifically in Asia and in the Mediterranean, which have cultural heritages basically of exploiting these species dating back centuries. So it's really a cultural thing for countries in Asia, specifically Japan, which consume about 80% of sea urchins worldwide. And pictured on the right is just a photo of some sea urchins at a market in Chile, which are the largest harvesters of urchins in the wild. And here are just some more photos showing how urchins are harvested. The middle picture is actually showing Tripneustes gratilla, a Palauan woman from the Philippines. And they're mainly just collected by scuba or traditionally snorkeling. So there are many countries that harvest sea urchins, obviously Japan, China, and Australia, Philippines, Fiji, and Japan are sort of the main countries that harvest Tripneustes. And now South Africa are looking into obviously establishing an aquaculture for this species. As you can see from this graph, catches have peaked at about 1995 at over 120,000 tons and have pretty much been decreasing ever since then due to overfishing and unsustainable harvesting of different species of sea urchins. The green bars show quite a drastic increase in the trend of aquaculture of different species of sea urchins. Worldwide, Tripneustes is being cultured in Australia, Japan, Philippines, and those are the main, I think, places for the culture of Tripneustes. In South Africa, Mark Cyrus has been doing quite a bit of research on this. In 2012, 2013, he developed a formulated feed, or they developed a formulated feed, and they found that they could, using an artificial feed, which was supplemented by 20% ulva, they could achieve international quality of sea urchin gonads, which had the right texture and color. And then also he found that you only needed to feed the artificial feed just before the urchins develop their gonads, and you could feed them on just ulva or green sea lettuce up until then. Also, there's been quite a bit of research on on finding the correct culture conditions for the larvae and for the adults too. So this graph is from the FAO, and it shows quite a dramatic increase in sea urchin imports into Japan. So since they're the largest consumers of sea urchin products, and even though they are harvesting their own sea urchins and growing their own sea urchins, there's still this huge increase in products into their country. So they have this massive demand that they can't even keep up with themselves. And with that increase, this is from the Aquaculture Association of Canada, they put together a graph of the increase in sea urchin-related aquaculture publications, and that's increased too. Japan have been culturing their sea urchins for several decades now, and it's quite recent that other countries have looked to aquaculture to try and supply this demand, especially in the East. And as you can see from the other graph too, with the increase in aquaculture, I think aquaculture can really bridge this gap between supply and demand while taking off the pressure of wild sea urchins, which are declining in the wild. So to sort of conserve them, as well as if an aquaculture industry were to be established in South Africa, it would be a huge economic benefit, since these are such highly lucrative species. They're the most expensive, I think, seafood products in Japan. So it's a huge economic benefit, as well as social benefits, since it creates jobs. So Tripneustes gratilla are tropical sea urchin. As you can see in the red, they mainly occur from the Indo-Pacific, from Japan to Australia, and on the east coast of Africa. In South Africa, their their southernmost occurrence is at Haga Haga near East London. And if the sea urchin aquaculture industry were to be established, it would be there. Also, I should just note that they're an ideal aquaculture species, since they're quite fast growing and they reach maturity within a year. What's the problem, and why have we not done this yet? Well, they have quite a long larval life cycle, and it's a feeding life cycle, so there's extremely high rates of mortality in the larvae and in the post-settle juveniles. And research in these specific stages is lacking in terms of developing ideal culture conditions for these several stages. So the larvae shown is just the different. They have a 2-arm, 4-arm, and then 8-arm Pluteus phase, which is reached just before they settle, and the larvae stage is roughly a month. And while they're eating, they eat a array of different phytoplankton species. So when they settle, this is what a pretty much newly settled urchin looks like. You can see their spines and pedicellarium. And then this is a 30-day, approximately 30-day post-settled juvenile. And the tube feet are dancing around. So my project aimed to determine ideal culture conditions, looking mainly just at different algal feeds and temperatures for post-settled juvenile sea urchins. So we looked at 5 different diatom feeds, since they eat benthic diatoms, 4 standard single-strain diatoms, and 4 Coconus nidicia and Nitzia, and then we also looked at Olvella lens, which is pictured on the right, and that's a different one since it's not a diatom at all. It's actually a crustus green macroalgae, and then we had a blank control too. And Olvella lens was chosen because it's had some success. It's used in Japan and Australia to mainly settle urchins, and I think it's also used in our abalone industry as a settlement tool. But so we were going to test growth and survival on this algae. We also looked at 2 different temperatures. Since it's a tropical sea urchin, its ideal temperatures are around 22 to 28 degrees. So the room temperature, which was probably the ideal for them, our experiment had a mean of 26 degrees. And then we also looked at a much lower temperature of about 20 degrees. And this had implications for if we do establish a sea urchin aquaculture farm in East London, where temperatures are averaging about 18 degrees, and if water is to be used adjacent to the farm, you'd want to know what's the lowest bounds of temperature, basically, that these post-settled urchins could survive at without compromising growth and survival, so as to minimize heating costs potentially for the water that's to be used. Then thirdly, we just looked at fatty acid composition between the different algal treatments, and this is really not my field of expertise at all. And the UCC chemistry department did the analysis for us. The methods were all done at the Department of Agriculture, Forestry and Fisheries in Sea Point, and the larvae were reared and spawned, or spawned and reared there. And then my experimental design consisted of petri dishes and five replicates per algal feed, per temperature treatment, and there were 10. We put 10 larvae into each dish We allowed them to settle in the dark, since that encourages settlement, and all at room temperature. Then I sort of assessed settlement, and then we put them at their respective temperature treatments. And observations were taken using a stereo microscope. I took photos of each of the urchins every 7 days for a period of 22 days, and we used the Nikon element spacing, like software, to make measurements of test area where we could infer diameter length, and that was used as a proxy for growth. And then survival was also monitored by counting the deceased urchins and then removing them. So, some results. This is actually not showing a difference between the temperatures at all, since this was the settlement that I just monitored before I placed them at their different temperature treatments. But we can already see some significant differences, and the mixed diatom community, I don't actually think I mentioned that earlier. The fifth diatom treatment was a mixed diatom community, and it was a naturally occurring community of diatoms. So we're not actually 100% sure what's in those, but they seem to do significantly better than most of the other treatments in settling them, obviously not in the other ones. And Nitsia and Coconis did not do very well in at the room temperature treatment, and that's due to a failure of they didn't coat very well at all. So I think that's why they died. It wasn't necessarily a reflection of the algae. But we can already see, so in the room temperature treatment, the Ovella lens did really well. It did significantly better than all the other diatoms. And unfortunately, we didn't have enough Ovella cultures to repeat them at the 20-degree one. So that's hopefully what we would be able to do in the future. But this is quite hopeful in terms of finding ideal feeds, and we've just shown that yes, you can use Ovella lens, and we can use it as a feed too, and not just as a settlement tool. So that was survival. This is growth. Ovella also did significantly better in growth, producing much bigger diameters than all the other ones. And you can also note that the mixed diatom community did slightly significantly better than the single strains of diatoms. And when you read the literature, seems to be a common thread that mixed diatoms generally do tend to do better than single strains. And this next slide may give a reason as to why. Like I said, this is not my area of expertise, but the mixed diatom community had significantly more percentage weight lipid content there than the other diatom species. Unfortunately, again, Ovella was not analyzed since you couldn't get samples in time, but it's also being done at the moment. I just don't have the results. So this could potentially be if there's more fatty acids, and fatty acids have been thought to play quite an important role in growth and survival and settlement. So maybe a higher content of them could significantly impact growth and survival of these sea urchins. The graph on the left just shows the different composition of fatty acids that were found, and although there were a couple of significant differences, they weren't necessarily all the same, that were different all the time. But the mixed diatoms weren't significantly different than any of the others in composition, and they all seem to have the fatty acids that were essential to sea urchin development. So just in conclusion, the Ovella produced the best growth rates and survival rates out of all the treatments. The mixed diatom community performed better than the single strain diatoms in settlement, growth and survival. And the temperature, which I didn't really discuss now, so I'll say it here, there were no significant differences between the two temperatures in growth or survival. So this looks hopeful in terms of establishing aquaculture industry where we're in East London, where maybe water would not necessarily need to be heated up to say 26 or 28 degrees. And the mixed item community also seemed to have significantly more percentage fatty acids by weight, but not necessarily in composition. So I think in terms of establishing an aquaculture industry in South Africa, there definitely does seem to be hope, and this is quite an ideal species to use. And yeah, thank you.